My name is Stanley, and I'll be presenting my thesis on raft polymerization in stereolithography. For my thesis, the main exploration of raft polymerization is in optimizing the mechanical, structural, and printing properties of raft polymer objects, and researching the comparative performance of the varying raft agents. The monomer and crosslinker used for this research were isobonyl acrylate and trimethylopropane triacrylate, both well suited to the task of UV curing due to their abilities to form highly reactive free radicals to initiate rapid chain reactions. The photoinitiator used was TPO, an efficient free radical Norrish type 1 initiator. The raft agents I worked with included BTPA, CDTPA, DPTTC, CPADB, DTC1 and DTC2, as well as a pH switchable raft, with the aim to test the effects of different activating and leaving groups on the structure of the printed objects. To begin, the kinetic study investigated the curing speed of raft polymerization. The method involved pipetting 200 microliters of the resin onto an FTIR ATR machine and characterizing between 400 and 4000 reciprocal centimeters for the absorbance in several intervals of time, integrating the polymer peak at 1650 reciprocal centimeters. Using this method, we firstly compared the monomer to crosslinker ratio and its effect on the kinetics. From here, we can determine that a higher monomer to crosslinker ratio resulted in a higher conversion plateau. However, the higher conversion led to a more brittle sample, making it hard to remove from the printer head without breaking. A 90 to 10 IBA to TMP-TA ratio was chosen as it allowed for the removal of the printed objects without breaking. Moreover, the addition of BTPA can be seen to slow down the polymerization reaction. Literature postulates this as either a result of slow fragmentation from the raft agent or slow reinitiation after the chain deactivation. The slowing effect was more pronounced when increasing the BTPA concentration, indicating that more raft agent in the resin would result in longer printing times. BTPA showed the best kinetics, allowing for printing speeds of 30 seconds per layer, with other samples printing in double to quadruple the time. CDTPA and CPADB did not print. Post-curing of 15 minutes was optimal as longer times did not contribute to significant conversions. A dynamic mechanical test was performed using the DMA Q800 to perform a single cantilever deformation testing to determine the tan delta of the raft printed objects. The interpretation of the tan delta determined the homogeneity of the printed objects, as evenly distributed networks would have similar interactions between chains, leading to thinner peaks. The tan delta values from the DMA data were normalized, with the full width at half maximum calculated to evaluate the effectiveness of each raft at producing a homogeneous network. Data showed only BTPA and DTC1 to be noticeably effective in reducing heterogeneity, with DBTTC barely inching out, all while other raft objects seem to be less homogeneous than the raftless species. Addressing the quality assurance, the switchable raft data is a result of the batch-based resin being different from the other 5, resulting in its noticeable variance, though despite this, its full width at half maximum was still lower than DTC2. The switchable raft shared a resin batch with BTPA at weight concentrations of 0.5% and 1%, where it can be seen that with increasing raft concentrations, the tan delta curve width decreases, suggesting increased homogeneity with increasing raft agents conforming to the hypothesis. Finally, a Mark 10 ESM303 tester was used to determine the Young's modulus and strength of the printed objects. Early deductions of the raft material being brittle suggests a high Young's modulus. This complied with the tensile data, where all the raft agents besides the switchable raft has a higher Young's modulus than the raftless composition, as seen by the highlights here. Furthermore, when varying the BTPA concentrations of the printed objects, the Young's modulus increases linearly. However, the strength of the printed objects were compromised by the inclusion of raft agents. The combination of weaker strength and more brittle systems meant that the object became fragile. Interestingly, despite raft supposedly weakening the object, increasing the concentration of BTPA slowly reintroduced strength back into the system. Addressing our earlier questions, the key takeaways from the experiments were that raft indeed assists in creating a more homogeneous polymer object in 3D printing. Despite this, it does not necessarily contribute to the betterment of the mechanical properties of the printed objects, as it increases the fragility instead, thus offering no trade-off for the decrease in printing speed. However, it seems that there is a possible space for further investigation into optimizing the raft agent concentration to reduce the deficit in strength. Thank you for listening.